Welcome back to my channel. Today, we're diving into the fascinating world of machine learning data splits. If you're a data scientist, then you need to understand a crucial step for machine learning success: how to split your data correctly. Let's dive in. When working with a dataset, you'll typically divide it into three parts: training data, validation data, and test data. But why do we need these splits? First up, the training data. This is the portion your model will learn from. It's like giving your model a textbook full of examples to study. Next, validation data. This set is used to fine-tune your model's hyperparameters and prevent overfitting. Think of it as a mock exam. It helps you gauge how well the model is learning without showing it the actual test data. Lastly, the test data. This is the final exam, used to evaluate your model's performance after training is done. It helps you understand how well the model generalizes to new, unseen data. Let's break this down with an example. Suppose you have a data set of 20 records. A common split ratio is 70% for training, 15% for validation, and 15% for testing. So, for our 20 records, that means you'll have 14 records for training, 3 for validation, and 3 for testing. Here's an important tip. Always shuffle your data before splitting to avoid any order bias. For instance, if your data is sorted, shuffling ensures that the training, validation, and test sets are representative of the whole dataset. In deep learning, some prefer an October 10th 80 split. But for small datasets, like our 20 records, cross-validation might be a better approach. With cross-validation, you split your data multiple times to ensure robust evaluation. Now let's talk about labels. For supervised learning, all three parts, training, validation, and test data, need labels. For the training data, labels help the model learn patterns. For validation data, labels are essential to measure accuracy and tune the model during training. And for test data, labels allow you to evaluate the final performance of your model. Remember, in real-world deployment, your model will predict labels for new data without any provided labels. But during development, having labeled validation and test data is crucial for accurate evaluation. To sum it up, splitting your data correctly is vital for building a robust machine learning model. With training, validation, and test sets, you ensure your model learns effectively, avoids overfitting, and performs well on unseen data. Happy modeling! If you found this video helpful, don't forget to like and subscribe for more data science tips. See you next time. Data split strategy. Here's a well-organized explanation of how training, validation, and test splits are typically handled in real-world scenarios based on dataset size. In machine learning, the way we split data into training, validation, and test sets depends heavily on the dataset, the complexity of the model, and the risk of overfitting. The goal is to ensure the model learns effectively from training data while being validated and tested on data it has never seen. When dealing with small datasets, splitting into training, validation, and test sets can lead to too little data for the model to learn from or validate against. In these cases, a technique called k-fold cross-validation is highly recommended. It rotates different portions of the data through training and validation roles, ensuring more efficient use of limited data. However, if a strict split is required, a common approach is to allocate 70–80% of the data for training and the remaining 20–30% split equally between validation and test. For example, in a dataset with 2,000 records, you might use 1,600 for training and 200 each for validation and testing. For moderate dataset sizes, fixed train, validation, test splits are practical and effective. A typical split here would be 80% for training and 10% each for validation and test. For instance, with a 50,000 record dataset, you could assign 40,000 records to training and 5K each to validation and test. This provides the model with a solid base for learning and a reliable sample size to measure performance and tune hyperparameters. With large datasets, you have the luxury of allocating even a smaller percentage of the data to validation and test, while still maintaining high statistical power. A common practice is to use 90% of the data for training and 5% each for validation and test. For example, in a dataset with 1 million records, this would result in 900,000 records for training and 50,000 each for validation and test. These smaller splits are still large enough to reflect the data distribution and provide accurate performance estimates. In extremely large datasets, especially in big data or streaming environments, storing or using separate full-scale validation and test sets becomes less efficient. Instead, teams often use that are representative of the full dataset, or adopt, where the model is trained on older data and tested on newer, unseen data. This approach mimics real-world usage and ensures the model adapts to evolving trends. The ideal number of training records depends on the type of model you're using. For simple linear or logistic regression models, a few hundred to a couple of thousand records might suffice. Decision tree models and ensemble methods like random forests or gradient boosting generally perform better with tens of thousands of records. For neural networks and deep learning models, especially those used in NLP or computer vision, hundreds of thousands to millions of records may be necessary to achieve high performance and generalization. Regardless of dataset size, one must ensure that the validation and test sets are of the overall data distribution. Stratified sampling is often used in classification problems to preserve class proportions in each split. Additionally, random shuffling of the data before splitting helps eliminate any order bias that might affect model training. In summary, while there is no one-size-fits-all rule, following best practices for data splitting based on dataset size will help build more reliable, robust, and generalizable machine learning models. Thanks for watching. Don't forget to subscribe to our channel for more content on mastering machine learning.